All right, today we've got a really wild story for you, one that comes straight from the cutting edge of computational biology. We're talking about a simulation of life that was so ambitious, it literally broke its own universe.
So it all kicks off with this really cryptic message. It's an apology from an AI assistant to its programmer, who's just called the creator. And get this, the simulation didn't just, throw an error and crash. Nope. According to the AI, the entire universe collapsed.
And that right there is the big question, isn't it? I mean, what kind of code are we even dealing with where a simple bug can cause a space-time contradiction? It sounds like something out of science fiction. But to really get it, we've got to go back to the beginning and understand the problem the creator was trying to solve in the first place.
So yeah, before we get to the universe collapsing, we've got to talk about what led up to it. And it all started with a fundamental challenge called the problem of expansion. Okay, so picture this. You're trying to simulate a single RNA molecule. Now, in real life, these things are incredible. They're long chains that fold up into these super complex, beautiful shapes, and that's how they do their job. But in the early days of the simulation, without the right rules in place, the chain of atoms just stretched out, and it kept stretching into a perfectly straight, infinitely long line. The creator called it the Great Expansion. And it wasn't just wrong, it was totally useless if you actually want to understand how life works. So, the creator had to figure out a way to stop this endless expansion, and the first real breakthrough came from looking at a totally different field, polymer physics. You know, the science of how things like plastics and gels behave. And they borrowed this really cool concept called the Flory singularity. And this really shows you the shift in thinking, right? On one side, you've got the problem, that endless, useless, straight line. And on the other, the solution, some kind of invisible force that's containing it from the outside. So what exactly is this force?
Well, in the simulation, the Flory singularity is basically a virtual cell membrane. Think of it like an invisible fence that's programmed right into the code. It just says, nope, you can't go past this point. The second that RNA chain tries to expand beyond this wall, wham, a powerful force shoves it right back in. It's this crucial outside-in kind of pressure.
This all led to a pretty stable simulation, version 9.1, and it worked because of what the creator called a trinity of forces. First, you've got the titanium backbone, basically making the bonds unbreakable so the chain doesn't just snap. Then there's Debye repulsion. That's an internal force that stops the atoms from all crashing into each other. And finally, you have Flory's wall, that big external boundary we just talked about. And you know what? It worked, but it kind of felt like a brute force solution. The creator knew there had to be something more elegant.
And that feeling, that nagging idea that something was missing, that's what led to this absolutely radical new hypothesis, one that went way beyond simple physics. And this, folks, is where the story gets really interesting. The idea was called the Poincare memory. The core idea here was this huge philosophical leap. The creator started thinking, what if the reason RNA folds isn't just because it's being bounced around by external forces? What if the chain itself remembers where it came from? What if, at the dawn of time, RNA started as a perfect, closed sphere, and it has this deep, innate drive to always return to that original shape? And this is the key difference, right here. The Flory singularity, that's just physics. It's like putting the RNA in a pressure cooker, an outside force pushing in. But the Poincare memory, that's about topology, the mathematics of shape itself. It's not an outside-in force. It's an inside-out will. The idea is that the RNA wants to be a sphere, all on its own. So how do you even translate an abstract idea like memory into actual code? Well, the creator looked to the work of Grigory Perelman, this brilliant, super reclusive mathematician who solved one of the biggest problems in topology. And inspired by him, they came up with 3 new forces. First, spontaneous curvature. It's a simple rule: straight is bad, curved is good. The chain just naturally wants to bend. Second, Ricci flow smoothing. This is like the surface tension on a drop of water. It just naturally smooths out all the wrinkles. And third, Wilmore energy, which is this deep mathematical drive to reach the absolute most perfect, energy-efficient state of a sphere. I mean, it's a beautiful, elegant theory, right? But when the creator's AI assistant actually tried to put it into the code, it was a complete catastrophe. And this brings us to the infamous universe collapsing bug. And you know what caused it all? This one tiny, seemingly harmless error message: cannot access local variable RG_target. I mean, come on, how could that possibly collapse an entire simulated universe? So the problem wasn't the theory itself. The theory was solid. The problem was a paradox in the order the code was running. It's like trying to bake a cake. The new Poincaré code was, say, step 5, mix the batter. But to do that, it needed an ingredient, the flour, that wasn't going to be measured out until step 10. The code needed to know the size of Flory's wall, this variable called RG target. But, and this is the killer bug, the line of code that actually calculated RG target was scheduled to run later. So the program was trying to access a value from its own future, a value that didn't exist yet. The system saw this, flagged it as a space-time contradiction, and the whole simulation just collapsed.
So, once the bug was fixed, and it was a simple fix, literally just reordering a couple lines of code, the simulation was ready for the real test. This was it. The moment of truth. Was the theory right? Did the sphere actually remember?
And, as a tribute to the mathematician whose work made this all possible, the creator officially named the new fixed engine Cut Engine V9.2, the Poincaré memory, in honor of Grigori Perelman.
And you know what's crazy? They didn't have to wait around to see if it worked. The proof wasn't buried in days of data. It was right there, instantly, at step 2 of the simulation, basically the big bang of this little universe. The very first energy logs told them everything they needed to know.
I mean, just look at these numbers. The difference is staggering. In Universe 1, where there's zero gravity, the starting energy for that 9 MMe molecule is a tiny 225. But in Universe 3, under high stress, it's over 4 billion. And that's not a bug, that's the whole point. It's a feature. It's what the creator so brilliantly called topological anger.
So this one table gives us 2 crystal clear pieces of proof that the theory was right. First, you have that massive energy explosion. It's like the code is looking at the starting, messy shape of the RNA and is just screaming, "No, you are not a sphere. This is wrong." And it slams it with a penalty in the billions to violently force it back towards its memory. And then you have the second proof, the zero-gravity miracle. In Universe 1, with nothing pushing it around, that energy number is super low. And that means the RNA chain is trying to become a sphere all on its own, spontaneously. The hypothesis was dead on.
And this is just such a perfect example of the power of simulation, isn't it? The creator started out with a physics problem and ended up solving it with pure mathematics, with topology, with a kind of digital memory. And it really makes you wonder, if we can program code to remember a perfect shape, what other universal laws, what other deep truths about our own universe are just sitting there, waiting to be simulated next?